So here we are. Today, let me pull up my notes. Okay, so today I'm covering, oh dear. Okay, hang on. Okay, covering hypothesis tests for two proportions. Okay, also covering type 1 and type 2 errors. Have you guys already covered type 1 and type 2 errors? Yeah? Okay, but we're going to cover it a little bit more deeply, okay? All right. Well, what can you tell me about type 1 and type 2 errors? Well, I'll go ahead and tell you then. So these are errors. These are mistakes inherent to the statistical process, okay? I don't know if I'm spelling inherent too correctly. This does not look right. How do?
1R.
1R. Okay, thank you. And really, they're inherent to not just the statistical process, but to our lives as a whole, okay? Also life. Anytime we have to make a decision about doing something, we're either going to decide to do it or decide not to do it, okay? And if you decide to do something, it could turn out to be a mistake by choosing to do that thing, okay? And if you decide not to do something, it could also turn out to be a mistake not to do something, right? So, perhaps, in the future, maybe not, someone, you may choose to propose to someone or someone may propose to you, all right? And at that decision, all right, you have a choice. You can say yes or you can say no, all right? And if you say yes, we're hoping that's the right choice and you live happily ever after. But it could also turn out to be a mistake and you don't know, all right? You can also say no and break the person's heart. And that might be the right choice because everyone will say like, oh yeah, that person was not right for you. But it could also be a mistake. And years later, you're like, oh, why did I say no, So these are just mistakes inherent to life and the statistical process. We've come up with these creative names, type 1 and type 2 errors, okay? So the type 1 error is basically we have decided to reject the null hypothesis, right? Okay, and we decide to reject the null hypothesis because our data leads us to this conclusion. Okay, but it turns out our data was wrong and we made the wrong choice, okay? Or not that our data was wrong, but it just turns out that our data was a bit unusual, okay? But it turns out this was the wrong decision. Okay, and type 2 error, so this could be something as like saying yes, but then it turned out to be wrong, right? Because up until this point, it seemed like this person was the right match for you, so you say yes to the proposal, and then it turns out that the data you had wasn't actually accurate portrayal of who this person was, or maybe the person changes over time, or something. I don't know, whatever, okay. So it could turn out to be the wrong decision. We don't know, okay? Type 2 error, on the other hand, is we decide not to reject the null hypothesis. Okay, and again, because our data leads us to this conclusion, and it turns out to be the wrong decision. And it's the wrong decision because in this case, the null hypothesis is actually false. Yes, we have a question.
Yeah, does that happen because you like chose like a really bad like significance level?
Well, it could happen. Well, that's one possible reason why we might have failed to reject the null hypothesis. Okay, it could be because we've chosen a bad significance level. It could also just be because when you take a random sample, the data that you have may not actually be a good representation of what's happening in the population. Okay, so throughout statistics, we have a population about which we are trying to make conclusions, and we are given limited data, and based on our limited data, we have to make a decision or make a conclusion. Okay, you guys have all this down? Can you guys all see this okay? All right, those of you in the back, great. I got some head nods. It's always encouraging. Okay, so we have learned that significance level, your significance level alpha, what is this tied to? Okay, yeah, so our decision to reject or not reject the null hypothesis depends on our significance level and how it compares to our p-value, okay? So our decision to reject or not reject the null hypothesis depends on the p-value and how that compares to alpha. Okay, so how does what is the p-value? The p-value is a probability, and it's the probability of what?
That you'll get an outcome when the null is true.
Yeah, that you'll get the data that we observed, or something more extreme, if the null hypothesis is true. Okay. Oops. Okay, so our data to reject or not reject depends on our p-value and how that compares to alpha. And the decision criteria is this. If the p-value is less than alpha, we reject the null hypothesis, okay? But the p-value is the probability of your data, probability of getting your data if the null hypothesis is true. So and so what this means is that even if the null hypothesis is true, if let's say our alpha is 5% and we end up getting a p-value of like 4% or something, okay? It means even if the null hypothesis is true, there's a 4% chance of our data coming about from random chance, right? So usually what we say is, well, our p-value is less than alpha, I'm going to reject the null hypothesis, okay? But it could actually turn out that the null hypothesis is true, and we just happen to get some slightly strange data, okay? We just happen to get some data that causes us to reject the null hypothesis based on this decision criteria, but that could be the wrong case, okay? So that is exactly what a type 1 error is, excuse me. So alpha turns out to be the probability of committing a type 1 error, okay? All right, well, we might say, well, if alpha is the probability of a type 1 error, well, I don't want to commit any type 1 errors, okay? So we say, okay, well, if you don't want to commit any type 1 errors, then just pick as small alpha as possible, right? Well, what would happen if we pick a tiny alpha? Okay, so, why not just pick a tiny alpha so we can avoid all type 1 errors? That is one solution to avoiding all type 1 errors. Okay. Well, what this happens is now we're almost never rejecting the null hypothesis, which means we are more likely to not reject the null hypothesis when we should. Okay, so reducing alpha will increase the probability of a type 2 error. Okay, and we'll often say beta is the probability of a type 2 error. Okay, and as researchers, we get to choose alpha. We get to pick alpha. There's kind of a default level of alpha is 5%. That's kind of the default. But we actually get to choose what alpha we want to use. On the other hand, we don't really get to pick beta. Okay. Okay, so beta is just kind of a consequence of a bunch of other factors, and we don't really get to choose that. But we do get to kind of affect our beta by increasing or decreasing alpha. So if we want to reduce our beta, we can kind of do it in an indirect way by increasing our alpha. And if we're okay with increasing beta, we can reduce our alpha. All right. Okay, so here's kind of an example. Or did I flip too quickly on the slide? We're okay? You want me to go back? We're okay. All right. All right. So imagine this. Okay. So we've got a criminal case. All right, in our court system. Okay. So this is the ideal scenario. Ideal scenarios. If the defendant is guilty, we're hoping that our court system will bring about a conviction. Okay. Okay. And if the defendant is innocent, okay, we want an acquittal, right? We want to let that person go free. I think 2 T's. Thank you. Thank you, my spelling muse out there. Okay, so we got the ideal scenario. All right, and then this is these are mistakes. Okay, now we don't want to make either of these mistakes, but there's 2 possible mistakes, right? So one mistake is if the defendant is guilty, the jury says not guilty. The jury acquits, right? So we don't want that. Okay, that's a mistake. All right. And then the other case is that if the defendant is innocent, and the jury says guilty. Okay, so both of these are mistakes that we don't want to make. Okay, ideally, there's enough evidence to bring about the proper decision, but in life or in court systems, we don't always have all the evidence available. Okay, and so we have to make a decision based on the evidence available. And based on that, we might not make the right decision. And so these are mistakes that are inherent to the court system. And okay, sorry, that's why it keeps And so these are mistakes inherent to the system. We want to avoid these, okay? Now, when you think about a trial, what do we say? We say the defendant is presumed blank, is presumed innocent until proven guilty, right? So because we're supposed to operate under the presumption of innocence, is our null hypothesis that the defendant is innocent or that the defendant is guilty? Innocent, okay? So our null hypothesis is going to be that the defendant is innocent, and our alternative will be that the defendant is guilty. Okay, so knowing this, which one of these is a type 1 error and which one is a type 2 error? We have a question?
Why not the other way around?
Why not the other way around? Okay, that's a good question. And the reason is because in our justice system, we presume innocence, and basically, if no evidence is presented, the judge is going to dismiss the case and say there's no evidence to say this person is guilty. Okay, that's how our justice system is set up. And it's not that the person is presumed guilty and now you need evidence to prove your innocence. Okay, and so because of this, we're always using evidence. The way our hypothesis tests always work is that we just assume the null hypothesis and evidence is presented, and if there's enough evidence, then we conclude that the alternative is true. But if there's not enough evidence, we just go on assuming the null hypothesis. Okay, so the burden of proof falls on the prosecution. Okay, so evidence is always used to support. So evidence or data, evidence and data are always used to support the alternative hypothesis, okay? And if there's not enough data, or if there's not enough evidence, we just continue assuming the null hypothesis, okay? So, that's why we conclude we do not reject the null hypothesis if there's not enough data. Okay, so going back, which one of these is a type 1 error and which one's a type 2 error? So defendant is guilty, the jury says not guilty. Type 1 or type 2? So type 2 error is our answer, and that is because a type 2 error is that we did not reject the null, we did not reject the idea of innocence, okay? So we say not guilty, even though the null is false. So type 2 error is not rejecting the null even when the null is false, okay? And this one over here, if the defendant is innocent and the jury says guilty, that would be a type 1 error, okay? Okay, and so there's always some debate here, okay? But the way our justice system is set up, which error is worse, the type 1 or the type 2 error? Like we don't want to make either of these mistakes, okay? But in setting up our court system, which error, like if we were forced to say, okay, if you have to make a decision, which side would we rather, which error is worse than the other? We would say type 1 error is worse, right? We would say it's worse to send an innocent person to jail or, possibly to death row, sentence them to death or her to death if the person is innocent, okay? And that would be a bad thing. Obviously we don't want either of these things, but we would say type 1 error is worse, okay? Okay. Type 1 error is worse, so do we want to use a large alpha or use a small alpha? Yeah, we prefer a small alpha. Okay, and And our court system actually says this, right? When they charge the jury before they go into deliberation, what do they say? They say, you know, before concluding guilty, you want to be sure beyond a reasonable doubt, right? So beyond a reasonable doubt basically says, don't go off a hunch, but you want to make sure that that you're really certain about this, okay? Now, if we wanted to avoid type 1 error completely, we would have a non-functioning court system. We would just say, okay, well, I don't want to ever convict an innocent person as guilty, so I'm just not going to convict any people, okay? I will never say guilty. That way I can die and have a clean conscience about ever convicting an innocent person, right? But we would say that's not a good system because now all the bad people who should be guilty will get away with it, right? So having a 0 alpha will, you know, clear our conscience of type 1 error, but that's a bad system, okay? On the other hand, you don't want to be the I don't know what the word is, but you don't want to say guilty to every single person who walks into your court, right? And because you might be able to die and say, well, now I can die peacefully knowing that every single person who was guilty, I made sure that person was punished, okay? Because I said guilty to every single person. But then that means you've convicted a lot of innocent people as well, okay? So having an extremely high alpha or extremely low 0, like a 0 alpha, is not good, right? So okay, so you know, like 0 alpha would lead to no convictions, okay? No type 1 error, but lots of type 2 error. Okay, and on the other hand, you know, max alpha, so alpha being 1, this would be all convictions. This will be no type 2 error, but lots of type 1 error. So it's a balance, okay? And it turns out, you know, kind of the balance that statisticians have agreed upon over the course of time is that 5% is a good rough number to use, okay? There's nothing magical about the number 5%, but that's kind of the number that has been agreed upon. Okay, so you know, we kind of have this summary table. Okay, so we'll say the truth, null is true, or the truth is that the null is false. And our decision, reject the null, or do not reject the null. Okay, so if the truth is that the null is true, rejecting the null, this would be a type 1 error. Okay, if the truth is that the null is false and we've chosen not to reject it, this is a type 2 error. Okay, over here, if the null is false and we reject it, this is a good correct choice, correct decision. And over here, this is also the correct decision. Okay, and so notice that at the end of a trial, if there's not enough data to bring about a conviction, the jury never says, we the jury find the defendant innocent. The jury always says, we the jury find the defendant not guilty, right? We the jury find the defendant not guilty. I should put the whole thing in quotes, not the not guilty part only in quotes. We the jury find the defendant not guilty. Does this prove that the defendant is innocent? No. Okay. Does not prove innocence. just says not enough evidence for a conviction. Okay, and that's why we never say, and in the same vein, we never say we accept the null hypothesis. Okay, let me just up here. Okay. Do we feel okay about all of this stuff? All right, so now let's get into hypothesis testing. Okay, and this is for proportions. And we have 2 samples. So you have already covered hypothesis testing for proportions, but in that case, you were dealing only with 1 sample. Okay, so in this case, we're basically saying, you know, we've got population 1, and we have population 2. Okay, we can't observe population 1; it's too big to be observed directly. So instead, we just take, we take a small, random piece out of it. This is our sample. Okay, so we get sample 1, and then out of population 2, we take a random sample and we get sample 2. Okay, and in sample 1, we observe something. We observe a p-hat, a sample proportion p-hat. And with sample 2, we observe a sample proportion p-hat 2. Okay? And these 2 proportions are most likely going to be different, right? If you take 2 random samples, even if you're taking them from the same population, it's very unlikely for you to get the exact same proportion both times. Okay? And so the question is, okay, if P1 hat and P2 hat are different, are they different enough for me to conclude that population and population 2 have different proportions? Or is it still possible for the 2 populations to have the same proportion? Okay, so we will observe, I'll say most likely observe, that P1 hat and P2 hat, or P hat 2, are different. Okay, so the question is, okay, these sample proportions are different. Okay, does that mean their respective populations have different proportions? Okay, or is it possible that the populations have the same overall proportion? Okay, so that the populations have the same proportion, and we just happen to get 2 samples with different proportions. And okay, so this is essentially the question that we are trying to answer when we are doing hypothesis testing for proportions with two samples. Okay, so so here's the example that we'll work through, and okay. All right, so far so good? Okay, I'm going to flip to the next slide. So what we have is, you know, here's our question, oh man. It's because I bumped the turn off button. All right, well, okay, so, it'll turn back on. I just have to wait for it to turn off, and then I have to wait for it to turn on. It's like, it's not a light switch. You gotta. Okay, so on your papers, right, is obesity increasing? This is our question. Okay, and here's the data that we have. So on your paper, you can write something like data, and you'll say sample 1. Sample 1, and the data for sample 1 is a random sample of 29,000 people. So 29,000, that's sample 1. It's still turning off here, okay? So random sample of 29,000 people, and in that sample, 24.4% of the sample were obese. Okay, and this was a sample taken in 2008. I really don't know what happened. It's still not letting me turn on. Okay. All right. So sample 2. Are you guys okay here? Maybe. How do I roll up the screen here? Okay. Okay. Sample 2. I'm going to just say. Also 29,000 people. This one has a proportion of 26.7% obese. Okay, and this sample was taken in 2013. Okay, so effectively, so if N1 is 29,000, and we have P hat 1 is, what is that, 24.4%. Okay, I should really do 0.244 because it's a proportion. Alright, sample 2, N2 is 29,000, and P hat 2 is going to be 0.267. Alright, so the question is, over here in 2008, my random sample showed 24.4% of people were obese. 5 years later, I took another random sample, proportion 26.7% obese. The question now is, are these samples, do these samples say that in the population, the proportion of obese people have actually changed? Or could it be that when I took random samples, I just happened to get different proportions? What do you guys think? Does it mean that the populations, oh look at that, populations are different? Or could it be that just because of random sampling, in 2008 I happened to get a random sample where there were less people obese. And in 2013 I happened to get a random sample where more people were obese. Okay? Well, this is the question we're trying to answer. And so using statistics, we can actually answer that question. Okay. The screen is back. Yay. Okay, so the question is, are different proportions. So we have different proportions, okay? Do they mean, or do they indicate that the proportions have changed? From 2008 to 2013? Or could the proportion in the population still be the same, be unchanged, and we just happen to get random samples with different proportions? Okay, does that question make sense? Okay, so that's what we're trying to answer. And so we're going to set up our hypotheses. So our null hypothesis will be that the proportion in 2008 is the same as the proportion in 2013. Okay? So this is the proportion that existed in 2008. Is that the same as the proportion that exists in 2013? Another way, this is just an alternate form that says exactly the same thing, is to say rather than that P proportion 2008 and 2013 are the same, we can say that the difference between them is 0. These two things say the exact same thing. Right? We can see that. Okay. One thing that's always helpful is that the null hypothesis will always have an equal sign in it. Okay, the alternative. The question is obesity increasing, right? So what would our alternative hypothesis be? We would, if we want to see if the answer to this question is yes, we would expect that the proportion in 2008 is what compared to the proportion in 2013? Less than, okay? Or the alternate form would be that 2008 minus P 2013 is less than 0. Okay. Do you guys use StatCrunch? Yeah, okay. So let me show how this would be done in StatCrunch. All right, so I'm going to go to StatCrunch. Okay, so in StatCrunch, the way we would do this is we would go to the menu Stat, then we would go to Proportion Stats, to sample with Summary, okay? Proportion Stats, 2 samples with Summary, all right? And so, wait, yeah, with Summary, how do I change this from, okay, yeah. All right, so we had sample 1, we had 29,000, okay? And what we had, how many obese people were in sample 1? Well, we would have to do, what was it, 24.4%, is that right? So I would have to do 0.244.
It's 7,776.
Okay, great, 7,076, thank you. Thank you, okay. And then, did everyone get that? 29,000 times, so basically you need a number of successes, or a number of observations, would be 29,000, and the number of successes, it's a funny word to use for obese people, but you know, we would do our proportion is 24.4% of 29,000. We would get 7076. Okay, and we would do the same thing for proportion 2, 29,000. 7. Huh?
It's supposed to be flipped.
It's supposed to be flipped?
Yeah, because there's 29,000 observations, not successes.
Oh, yeah, you're right. Okay. 7076, 29,000. Thank you. 7743, 29,000. Okay? This is, we're testing for P1 minus P2 equal to 0. And then the alternative would be that P1 minus P2 is less than 0. Okay? Is this okay? And then so we click compute. What do we get? This is what we get. How do I copy this? Okay, so these are my results.
Hello?
Hello? Okay, so this is these are the results of our proportion test. We get a p-value of negative 0.000. You know, this is a tiny thing, right? Look at our z statistic. It's over 6.6 standard deviations away from the mean. Okay, or 6 standard errors away from the mean. And you guys learned the empirical rule that said anything over 2 is unusual. Anything over 3 is really unusual, and this guy is over 6 away. So this is like ridiculous, okay? So even though the proportion difference between 24.4% and 26.7% doesn't seem to be that huge, when we do the statistics behind it, it's actually a huge difference, okay? This result is almost impossible to happen just from random chance. So is it possible that the proportion of obese people hasn't changed and we just happen to get these crazy samples? Technically, nothing is impossible, okay? But it's so incredibly unlikely that we are going to say, I'm almost certain it didn't happen by random chance. I'm going to reject the null hypothesis. Okay? Yes, question?
How do you find p-value without sign approach? Or should you just use it?
Yeah, in the book it like tells you to do.
Yeah. Okay. So,
back using the z-score, but, like,
have you ever used a table to get your p-value?
we got it for the like the z-score using.
Okay. All right. So I'll give you the formulas, and it's not that bad. You just need to figure out all of your data labels. Okay. So anyway, let me just write this very quickly. Okay. So our p-value is crazy tiny. Okay. It's tiny. So this means, you know, is it possible for the proportion to have remained unchanged? And we got crazy samples. The answer is technically yes, but incredibly unlikely. Okay, so we reject the null hypothesis. Okay, we conclude that the alternative must be true. Or we conclude that our data supports the alternative. I shouldn't say that we conclude that the alternative must be true. We conclude that our data supports the alternative hypothesis, and so we say we have evidence that obesity is increasing. Okay. So we have this. All right. How would we get our z statistic and our p-value if we didn't have StatCrunch? Okay, this is a great question. I'm going to just throw up a bunch of formulas here. Okay, so you will need 6 values. Okay, and they're not too bad. You will need 3 from sample 1. So sample 1 would require the sample size n1, y1. This would be our x1, I should say. The successes. Or actually, you only need 2, okay? N1 and X1 and everything else comes together, and you'd have P hat 1, which would be X1 over N1, okay? And from sample 2, so really you just need these 4 because this one comes from the other 2, okay? N2, X2, and P hat 2, okay? X1, X2 over N2. Now, in our example, I gave you the p hat, and you had to get your x, okay? In other problems, they might give you the x, and you have to get the p hat, okay? So really, you do need these 6 values, except they might only give you 4 of them and expect you to figure out the other 2 on your own. But we could do that, right? Okay, so then to get your z statistic, you have to calculate some intermediate values, okay? So we have a p hat overall. And this is just the overall proportion if we threw all of these observations together. Okay, so the p hat overall would be x1 plus x2 together divided by n1 plus n2 together. Okay, this would give us a p hat overall. So these are kind of your next steps in the calculations. Okay, so step 1, get these values. Step 2, get your p hat overall. Step 3, once you have your p hat overall, which I'm just going to abbreviate to be p hat because I don't want to have to write overall every single time, you're going to get your standard error. And it's really just a matter of plugging in values into these equations. So you use your p hat, this is the p hat overall, times 1 minus the p hat overall. These are just ugly formulas. We can't really do anything about that. Okay, the smart statisticians figured this out for us. We have to thank them for their work that they came up with this formula, even though it's a little bit ugly. Okay, so this is what we have. You get your standard error. Okay, and then now we're going to get our z-score. And so your z-score is you take the p hat 1, you subtract off p hat 2, and you divide your standard error. Okay? All right, and then I know I'm going just a minute over our time. So to go from, so yeah, this p hat, this is the p hat overall, okay? Okay, so those are the p hat overalls from step 2, okay? I promise, when you read the problem, if you label your 6 values as such, everything's going to be a breeze just because you're just plugging in values. Okay, so then lastly, to go from your z-score to a p, or to a p-value, okay? So if the alternative has a greater than sign, your p-value is the area to the right of z. Okay, and we know how to do that, right? Okay, and if your alternative has a less than sign, your p-value is the area to the left of z. Okay, and then if the alternative has a not equal sign, you find the area away from 0, so that's the tail area times 2, okay, is equal to your p-value. The tail area is the area away from 0. Have a good weekend. Okay, I hope this is all right. Thanks for bearing with me a couple extra minutes. Have a great weekend. I probably won't see you guys again, but maybe, who knows? Maybe some of you are stats majors and I'll see you guys in the stats department.
But isn't it like
Thank
this
you.
and then
All right.